In this video, we're going to look at a randomized experiment to explore the effectiveness of acupuncture in treating chronic lower back pain. So it was a nice big study, over 1,000 patients randomly assigned to one of 3 treatment groups. One of them was assigned to Barium acupuncture, so like real traditional Chinese medicine. One was assigned to sham acupuncture, which, if you're wondering what that is, there's still needles involved. It's still safe and clean. That should be important to mention. But basically, they're not targeting specific areas like they would be in real acupuncture. So this is the placebo. And the third group is non-acupuncture therapy. So this doesn't mean that they got no therapy. They just got drugs, physical therapy, things like that. Notice that we have 3 groups here, so this variable is not binary. We wouldn't have been able to analyze this with the tools that we learned in Chapter 5, but Chapter 8 we're going to be able to compare more than 2 proportions. And for each patient, the researchers just recorded whether there was a substantial reduction in pain or not. So here we are looking at a binary response. So let's start by writing the hypotheses. So we can write it in words in terms of an association. So we can say that there is no association here between our 2 variables. That would be the null hypothesis. So for this example, no association between the type of treatment, which type of acupuncture they got, and the reduction of pain reduction. So that would be our null hypothesis, that knowing which group they were in doesn't help you predict whether their pain was reduced. We can also write this in symbols, and because this is categorical data, we're going to use pi for our symbol, but we're actually going to need 1 for each group, right? We're comparing 3 proportions here. So we have the proportion who improved with the real treatment, and we want to know whether that's equal to the proportion who improved with the sham treatment and the proportion who improved with the non-treatment. So we're just setting all of them equal to each other. So this is saying that all of the treatments are equally effective. Notice it's not saying that none of them work. It's just saying that they all work equally well. The alternative hypothesis is just that there is an association. So we're doing all one test here, so we're not able to say specifically which of these treatments are different from each other, just that they're not all the same. So we write our alternative just as there is an association between type of treatment and pain, or if we want to write it in terms of pi, I would just write at least 1 pi, so at least one of those proportions is different from the others. So what about in the sample? Is there any evidence of an association in the sample? So what we're going to do is we're going to look at how many had pain reduction in each of these groups. So for the real acupuncture group, there were 387 people randomly assigned to this treatment, and 184 of them had their pain reduced. So this would be 0.475, a little bit less than half. And we could do the same thing for the other groups, and we can see that for sham, that proportion is 0.442, and for non-acupuncture therapy, that proportion is 0.273. So they're not all the same. Knowing what group someone is in helps you predict whether their pain was reduced or not. So we would say yes, in the sample at least, there is evidence of an association. So we want to conduct one test that will look at all of these proportions at once. Why do we do that? Why not just set them up as 2 proportions equal to each other and then use the methods that we learned in Chapter 5? The reason comes back to type 1 errors. So if you remember, when you look at your alpha level, you're basically setting the type 1 error rate that you can handle. So alpha is the probability of a type 1 error. And if you're looking at the probability of a type 1 error being equal to alpha, that's really meaning in just one test. So like let's say you set it at 0.05 and you conduct one test, there's a 5% chance that you'll make a type 1 error. But if we do more tests, then it's going to start to pile up. So like here, if you want to test each of these pairs on its own, we call these pairwise tests, you're going to have to do 3 separate combinations, right? Real sham, real non, sham, shouldn't say shame, sham non. So we have to do 3 tests. And if we do 3 tests, that's going to add up, right? The probability of type 1 error is going to add up. So if we do 3 tests, we'll say the probability of at least 1 type 1 error is not going to be 0.05 is going to be greater than our alpha level. So we want to control that. We want to have one test where we know what the probability of a type 1 error is, and so that's why we want to do just one test as opposed to pairwise comparisons. So to conduct that test, we need a statistic, meaning a single number that we can calculate from the data that summarizes all of the evidence against the null hypothesis in our sample. So we can't just use counts. There's way more than one count. Even when we calculated proportions, we had to have 3 proportions. We can't just do the difference of proportions because we have more than 2 groups. So we have to go back to a statistic we used a long time ago, the Chi-Squared Statistic. So if you remember, the Chi-Squared Statistic is the sum of the observed count minus the expected count squared over the expected count. And the formula for the expected count that we're going to use is the one that we learned in Chapter 5. So remember, the formula for the expected count is that the row total times the column total divided by the overall total will give you the expected count. And when we say expected here, we mean what we would expect if the null hypothesis were true. So in this case, what would we expect if there were really no association between the type of treatment you got and whether or not your pain was reduced? So I won't calculate each of these by hand, but let me go ahead and show you how to do it for the first cell, just to remind you. So we're taking the row total times the column total divided by the overall total, and that's going to give us the expected count that would go in this first cell. So we do 461 times 387 divided by 1162, and we get the expected count in that cell, which is 153.5. And we don't want to round these. When we say expected, we really mean what we would expect on average, so those don't necessarily need to be whole numbers. If you notice for sham, that's going to turn out exactly the same because we have the same sample sizes for real and sham, so the row, column, and overall totals will be the same, and that's 153. And then from here, we could keep using the formula, but we can actually figure out the rest just by subtraction. So we're going to call this a table with 2 degrees of freedom because putting in 2 numbers is actually enough to figure out the rest. So we could just subtract to get the other numbers. So if we did 461 minus 153.5 minus 153.5, that would come out to 153.9. And notice it's very similar to before because the sample size is very similar to before. And we can subtract again to see how many we would expect to not improve. We get 233.5 in this group, and it'll be the same here, 233.5. This one just slightly higher, 234.1. So to calculate our Chi-Squared statistic, we're going to do the observed count. That's like the real data. So for the first cell, that would be 184. That was the count in the real acupuncture group that actually did feel better, minus the expected count, 153.5 squared, over the expected count, 153.5. And that uppercase sigma means that we're going to do this for every cell and add them all up. And I'm going to be too lazy to write it out for every single one, so I'm going to skip to the last cell, the non-acupuncture group, the ones who did not improve. So for that cell, the count was 232. The expected count, pretty similar, 234.1, and we square that and divide by the expected count again, 234.1, and we end up with a Chi-Squared statistic of 38.054. So we've learned in the past that when you have a large Chi-Squared statistic, that means that you have strong evidence of an association, which makes sense if you think about what the Chi-Squared statistic was actually measuring, right? It was measuring the difference between the actual data and what we would expect if there were no association. So the bigger those differences are, the stronger the evidence of an association. But we still have this question, right? Is Chi-Squared equals 38.054? Is this number that we got, is this large enough to be convincing? Right, so before we can decide that, we need a null distribution. We need to know what kind of values of the Chi-Squared would occur just by chance, and is this out of the ordinary enough to convince us that there's actually an association.